In the last class we started with what is two dimensional nosy experiment. We saw the basic idea behind that, what is nuclear over-Hauser effect. The idea in a nosy spectrum is to capture cross peaks between two atoms which are less than 6 angstroms, typically 5 to 6 angstroms, and we use the method of polarization transfer to do that, and this is through space interaction. That means there is need not be any direct through bond interaction between the two atoms. So, any two hydrogens which are close in distance between less than 5 to 6 angstroms can be studied by this spectrum experiment, and it is a very useful technique for determining structures of molecules, because when we talk about structures in general, structures means we want to look at distance between atoms, and the distance between atoms you have to obtain by only this technique of nosy. Very difficult to obtain distance information by any other method, and this is therefore a very direct approach to calculate the distances, and by using distances we can get structure. So, let us continue a little bit on how does this nosy experiment work, because this is one of the very important experiments in NMR. So, one should therefore grasp the basics of this experiment. So, this is the pulse sequence which is shown here. This includes 3 pulses. So, this is what is a schematic drawing here. So, what we do is we have a 90° RF pulse which is applied on the proton channel, that is on the hydrogen. Then when it moves after excitation, there is a T1 evolution. So, this is similar to what we have been doing in all the other experiments. So, once you do that, you allow it to evolve. So, this is what we will see mathematically shortly, and then you apply one more 180-90° pulse after some time, and after application of this pulse, what happens is the magnetization vector comes to the minus z axis. Once this happens, it starts now relaxing back towards the positive z by T1 relaxation. During that period, that is during this period, when it is relaxing back to z axis, we start transferring the polarization to another spin B. So, suppose this is spin A, it has brought to minus z axis. During this period mixing time, that is this is called mixing time, during this period it is transferred to spin B by the effect of NOE, nuclear over-Hauser effect. So, this is basically the idea, that you use a certain duration, allow this certain duration for during this period, allow the spins to mix with each other. And when we do that, after some time here the magnetization has come to B, that is the z axis minus z of one spin A has gone to minus z little bit to of another spin B. Now, this transfer depends on a variety of factors. Number one factor is of course the distance between the two atoms. If spin A and spin B are not very close, they are far away, then spin A cannot transfer its polarization to spin B. And second factor which matters is the mixing time. So, if you take a very short mixing time, that means you do not allow the two spins to interact for sufficiently long time, then you do not expect the spins to be transferring energy to each other or polarization to each other. So, therefore, you have to give some sufficient delay, but too much delay also is not good idea because of several factors which we will see later. So, therefore, the total there is an optimal value typically we use for this delay, and this is typically for small molecules is in the order of 200 to 500 milliseconds, and for proteins, let us say biomolecules, larger molecules, peptides, it will be of the order of 100 to or 60 to 150 milliseconds. So, this depends on the size. So, we will see that factors what governs the mixing time later. So, the basic idea is during this period the two spins are allowed to interact with each other through space, that is through the dipolar coupling method, which is basically responsible for nosy effect, and during this period the magnetization is transferred. After the magnetization is transferred, you apply a one more 90° pulse, which now brings the spin B into xy plane, and then it starts evolving. This is called evolution. This chemical shift starts evolving, and that is captured by detector, and that is known as an FID. So, basically what has happened is we started from one spin A, we allowed the frequency of the spin A to evolve. So, the information of spin A is captured here through chemical shift evolution, and that polar magnetization of spin A is inverted, and during the inversion the information of the chemical shift is carried along with it, because whatever happens during this period, that is the modulation because of chemical shift, that modulates the intensity of the peak, means it affects the intensity of the peak of the spin A, and that intensity is now stored information in this particular vector. And therefore, when it mixes, that means when it transfers from A to B, and B is now bring to xy plane, the information which is coming all the way from A is transferred to B, and then B will start evolving with its frequency chemical shift. So, basically what we have done is we have connected the chemical shift of one spin with the chemical shift of another spin by doing this mixing. That means only those chemical shifts which are mixed or which are transferred from one to another during this period, only they will give rise to cross peaks in the final spectrum. If two spins are not interacting with each other, means they are far away more than 5 or 6 angstroms, there will be no interaction between them through space, and therefore, the energy of the magnetization of A cannot be transferred to B, which means in the final spectrum you will not expect to get any cross peak between A and B. So, this is a very simple idea. You first allow just a general idea of 2D, which we have seen in the case of also Toxie and Cozy, is that you have a first period where you allow one spin to evolve in chemical shift, then use a mixing time, that is mixing pulse, which mixes the magnetization, and then it gets transferred to the second spin. So, let us see more in detail the mathematical part of this. So, this is what is shown here by the vector diagram. This is called a vector diagram. So, you start from spin A magnetization, which is along z axis, because before any pulse is applied, it is called relaxation delay, means you allow the spins to relax back to complete equilibrium. Then you apply this pulse, this is 90-degree pulse, this brings the spin A into the xy plane, and during this period it evolves because of chemical shift, and that evolution is represented mathematically as cosine of omega T1. Omega is the chemical shift. Now, during this mixing period it comes to minus z, and then it transfers to B because of NOE, and then as we said, as after the last pulse is applied, this now the spin A energy as polarization has gone to B, and now B is brought to the xy plane, which is shown by this blue, and the B will start rotating in the xy plane by chemical shift. So, what basically we have done is we have got captured the FID contains now this term and this term together. So, if you recollect what we saw in the case of the theory of 2D in the last few classes, when you multiply these two, that is the FID, and it has now two chemical shifts connected to each other, omega A in one dimension, that is T1, and omega B in the second dimension, which is T2. So, if I plot a 2D spectrum, I will get a cross peak between A and B. But remember, as we discussed in the last classes, that it is not that the entire polarization of A can be completely given to B. It is only a percentage of A polarization goes to B, the remaining 90% remains on A itself. So, that means during this mixing period, A just transfers only 5 to 10% of the polarization to B. That is a kind of efficiency you would expect at best. So, therefore, when you apply the last pulse, you not only have the B magnetization, but you also have the magnetization from A, which was not transferred at all. So, that will also evolve as cosine omega A T2, which is not written here, but you can think of it that when the second time again A will evolve, because A's polarization has not been completely transferred to B. So, that will cause a diagonal peak, because during both T1 and T2 it has omega A and omega A, because that will be the non transferred part of the magnetization. So, that is a diagonal peak, and then you get cross peak, which is A. So, as far as the analysis or interpretation of NOESY is concerned, we never care for the diagonal peak, we only worry about, or we are only look at the cross peak. Why is that so? Because diagonal peak anyway does not have any information, it is only telling me that A remains on A, which has nothing interesting to say, but A going to B is lot of information, because that tells me that A and B are now close in space by less than 5 to 6 Armstrong. So, just an observing a peak in noisy spectrum itself tells us that there is a distance information, because only if they are less than 5 to 6 Armstrongs you would expect them to show any interaction. So, we will go further, we can see an example here. So, this is a propyl chloride, this is the same molecule which we saw in the case of toxy. So, we will take the same example here. So, here let us say again ignore the J multiplet pattern, you basically get 3 peaks, because there are 3 types of hydrogens. So, we are looking at the hydrogen proton spectrum, and then let us say based on the electronegative effect, that is shielding, electron shielding inductive effect, A will be the most downfield shifted, B will be the second is the third, and the third will be the last. So, this is what is shown here. So, now I draw a 2D spectrum here. So, now we will look at how the noisy cross peaks or noisy spectrum will look like. So, first remember always we get a diagonal peak in NMR, this is in homonuclear proton and proton experiment. So, if you see in this case the 3 to 3 is here, 1 to 1, 2 to 2 and 3 to 3. So, this is always the case, because we can never transfer complete polarization or magnetization from one nucleus to another. Okay. So, now let us see the cross peak. So, in this case if hydrogen 1 and 2 are close in space, so how much will be this? This is only about 3 bonds away, and remember one bond is typically around 1 Armstrong. So, if you say the 3 bonds are together within 3 Armstrongs, 3 to 3.5. So, obviously they are less than 5. So, I would expect a cross peak between 1 and 2 in a noisy spectrum. So, this is what is schematically drawn here. Now, similarly between 2 and 3 I expect a cross peak, because 2 and 3 are also not far away, they will be again within 3 to 3.5. So, 2 and 3 also will show a cross peak in a noisy spectrum. Now, if you see 1 to 3, they also are not going to be far away, because if you look at the 3 dimensional structure, which we have not shown here, but you can, if you imagine a 3 dimensional structure, this will be also within 5 Armstrongs. This is not very far away, even in the case of a real 3 dimensional molecule. So, therefore, I would expect a NOE between them, and that is also will show up in the noisy spectrum. So, you see this looks like a toxy experiment. Remember in toxy also we saw that 1 to 2 is J coupled, 1 is J coupled to 2, 2 is J coupled to 3. So, 1 to 3 will get J coupled through intermediate 2, and we saw a 3 by 3 cross peak pattern, same thing here. So, then what is the difference between noisy and a toxy? Two things. Number 1, in noisy of course the transfer was not through J coupling, it was through space. Okay. So, therefore, the intensity of these peaks will be proportional, as we will see next slide, it will be proportional to the intensity, the distance of the peaks between the atoms, inversely proportional. So, we will see that relation more carefully in the next slide. So, now let us see what is the difference between a noisy and a toxy. Now, suppose imagine that your actually molecule had something like this structure. Okay. So, where this was a long chain, there was something else, we will ignore what was here, but there was a long chain and the whole molecule turned around, folded, and there was a methyl group here which we will label it as 4. So, this is just an example which I am trying to show you that how is noisy further different from toxy. So, now this 4 let us say has a 1D proton peak shows here is a methyl group. So, it will be expected somewhere between 0 to 1 ppm. So, let us say it comes here. So, now because of the structure of the molecule there is a fold here, this is called folding. So, when the molecule has folded, it has this atom has come close to this number 1, and therefore, I would expect a cross peak in noisy between these two atoms, because they will be very close to each other and they may come with less than 5 to 6 Armstrong. So, if I see a cross peak like this between 1 and 4, immediately I can say that I can conclude that there is a distance of less than 5 to 6 Armstrongs between 1 and 4, but this will not be possible to see in TOXI. So, this peak would not have come in 2D TOXI. Why? Because 1 and 4 are far away and therefore, are not part of the same spin system. Remember the word spin system which we defined in the case of a TOXI spectrum. Spin system is a set of spins which have some J coupling within between each other. Not all of them are coupled to all, but there is no spin which is not coupled to any other spin, means there is no isolated spin. So, that is that set of spins which are all having coupling within them is spin system. So, this does not obviously belong to this spin system which is these 3 hydrogens, because by bond it is very far away, but NOESY will give you that because it is close in space. So, this is how NOESY helps a lot to get the structure information which you would not have got from TOXI. So, that is why NOESY occupies a very important role in NMR spectroscopy because of this feature. Now, how do we get the distance information? That is what is shown here, and again we will see in the next slide that the intensity of cross peaks are very important in NOESY. The intensity means the volume, the area of the peaks. If I integrate this peak, whatever area I get has some relation with respect to distance. Okay. But remember, as I said, diagonal peak intensities are ignored because diagonal peak has no information. It is only telling me this 4 is come to closer to 4. What is that going to help us? No, how it is not going to help us. Similarly, 3 is with 3. So, that has no additional. So, diagonal peaks are ignored when intensities are concerned. In fact, diagonal peaks are a problem in life because you want, suppose there is a peak somewhere close to the diagonal, it will be covered by this diagonal. Remember, diagonal peaks are very strong in NOESY. We will down the line we will see some real spectrum, but this is just a schematic. But typically what happens is the diagonal peak in NOESY spectrum is very strong, typically about almost 100 times stronger, 50 to 100 times compared to the cross peaks. So, that means if intensity of this is 100, the cross peaks will be only about 1 or 2, and therefore, if this intensity some peak is, let us say, comes very close to diagonal, it will obviously be hidden or covered by the diagonal peak. So, getting a diagonal less without diagonal NOESY itself has been a focus of research in NMR spectroscopy over the years. Several papers, research publications have been published where people have tried to design a diagonal less NOESY and NOESY without diagonal, because peaks which are close to diagonal can now be then observed that were not observed if there was a strong diagonal present. So, these are the basically the ideas behind NOESY. Now, let us see how the distance information is used comes from the intensity. So, as I said in the last slide, the intensity of the cross peaks in 2D NOESY is related to the distance between 2 protons and as well as the mixing time. Okay. So, we will see the effect of mixing time a little bit later. Let us look at how the distance between proton varies with distance with intensity. So, this is the very famous formula. I is intensity, that is volume. So, when we talk about intensity in NMR, we say typically we imply area. So, keep that in mind, that area and intensity or volume of a peak can also be a 3-dimensional structure. So, the volume of a peak is intensity, they are all kind of interrelated. Okay. So, the intensity is proportional to 1 by r to the power 6, and as far as mixing time is concerned, intensity is directly proportional to mixing time. But there is one phenomenon which known as spin diffusion, which we will discuss a little bit later, which spoils this equation. It does not, we should not have spin diffusion. Only if there is no spin diffusion, intensity will be directly proportional to mixing time. So, we will talk about spin diffusion a little bit later. So, let us remain on this here, that intensity is proportional to the inverse 6th power of distance. So, therefore, from intensity or volume of the peak, distance can be calculated. I would stress on this fact that we actually do not calculate like this, we use the word estimated. So, that means I would say the peak of the based on the intensity of the peak, the distances can be estimated. Okay. So, because of this 1 power r 6, you see this goes as r to the power 6, the intensity falls rapidly with distance increase in distance. Therefore, we use a cutoff of 5 to 6 angstroms is because if you go from 6 to let us say 8 or 7 Armstrong, the intensity will fall very rapidly, because 1 to the power 1 by 6 to the power 6 versus 1 by 7 to the power 6, 7 Armstrong, when r is equal to 7 whereas r equal to 6, if you can see compare, there will be an order of magnitude difference. Therefore, this order of magnitude difference, the peak intensity falls by 10 times if I go from 6 to 7 Armstrongs. Therefore, we say that there is a sharp kind of a decrease in the intensity of the peak as the distances increase. So, therefore, this is a very interesting thing. Because of this, we can safely say that peaks which are seen in the NMR NOESY spectrum means they are within 5 to 6 Armstrong. Now, as I said in the point here, this exact distance cannot be calculated accurately from NOESY spectrum. So, this is a big issue. There are many reasons for this. So, what are the ways to come out of this? There are two ways. Number one, like we do for chemical shift referencing, you can take a fixed distance. Let us say you have a molecule, if let us say you have a system in your molecule, like let us say an aromatic system in your molecule. So, remember in aromatic is a very rigid planar structure. So, the orthoprotons, if you look at, let me draw the structure here. So, if you have an aromatic spin system like this, as aromatic moiety in your molecule, let us call this H1, H2. Typically, this distance is fixed. Why is it fixed? Because remember, according to chemistry, this is a planar structure and there is a sp2 hybridized carbon, and this angle cannot keep fluctuating. So, if the angle cannot be fluctuated, that means it is fixed angle. So, obviously, these two are at a fixed distance from each other. Even if this whole aromatic molecule rotates, how does it rotate? Remember, in molecules, typically it rotates around. So, so in a molecule it rotates around this axis. Okay. So, this is the axis of rotation typically in any aromatic system. So, this rotation will only change the distance between this hydrogen to some other hydrogen, but between the two hydrogens which are marked here, the distances between H1 and H2 are fixed even if there is a rotation. So, therefore, this distance, if I know the distance, how will I know the distance? We know it from standard geometry or structure of any aromatic molecule. So, and if I see a cross peak between these two atoms in the NOESY, which I expect to see, because these two atoms will definitely be less than 5 Armstrongs. Okay, you can calculate yourself with taking some values, and therefore, if I know the distance and I know the intensity of the cross peak, then I know that this relation will hold. So, then I take a ratio. So, suppose now I have unknown atoms, two unknown atoms whose distances I want to calculate between them, but I know only the intensity, I do not know the distance. So, you can see here for a fixed reference molecule like this or moiety like this, I know I know R. Okay. Now, for the unknown case, I know I, that is from the NOESY spectrum, but I do not know R. So, that is R is what I want to calculate. So, if I simply take a ratio, then I by I reference will be equal to, in fact, you can either say proportional or I would say equal to. So, I upon I reference, where reference is the intensity between these two hydrogens, is equal to R to the power 6 reference, that is the distance between these two hydrogens, divided by the unknown distance. So, now from this equation I have three knowns. I know this from the spectrum, I know this from the spectrum, I have this from the structure here, and this is what I need to calculate. So, this is one way to calculate distances between atoms based on a reference. So, similar to what we do in case of TMS, remember in NMR everything is with respect to reference, there is nothing like absolute things in NMR, everything is relative to something which is we call as a reference. So, therefore, here also we use a reference. Now, this is one option. The second option is that you do not calculate distance like this, you simply say that look, I am seeing a distance, I am seeing a cross peak between two atoms. Okay. So, therefore, it has to be within 5 Armstrong. So, an example, let us go back to the previous slide, which is here. We saw that these two atoms or these two cross peaks are coming from interaction between these two. So, the fact that there is a cross peak between these two atoms immediately implies that it has to be within 5 to 6 Armstrongs. So, you see I already have some rough distance information from this kind of analysis. So, therefore, exact distances may not be required. In fact, we will see that down the line when we look at the application of NMR for structure determination, you really do not need exact distances between two atoms from nosy. All you need is just an information whether they are close or far. In the sense both are going to be, of course, every atom, the moment you see a cross peak in nosy, remember they are less than 5 to 6 Armstrongs, but within less than 6 Armstrong there can be a variation, it can be 3, it can be 2.5, it can be 4 or so on. So, what typically a large number of people do is that just qualitatively looking at the intensity, if it looks very strong peak, we say it is very short distance, if it is very weak peak, we say it is long distance, but long distance means still within the limit of 6 Armstrong. So, this is a qualitative way to estimate the distance, and that is also fine, because this procedure of using a reference and so on may not work always for a given system. You may not have aromatic at all. So, that you cannot, because this is the only system where distances are fixed. No other moiety molecule is difficult to have as a known reference in their same molecule. So, these are the different ways of how intensity and distances can be related. Now, let us see how is the effect of mixing time coming into picture. It happens like this. So, again we are looking at the intensity of the cross peak. So, for any given two atoms, that is that suppose I keep the distance and I vary the intensity now, the mixing time. So, remember if you go back to this slide, here intensity is proportional to distance. So, for a given two atoms, any two atoms, the distance is, how does that mixing intensity now vary with mixing time. So, we are not varying the distance, we are only varying the mixing time. So, if the mixing time changes like this in the horizontal axis, the intensity, or in other words the volume of the peak, shows this kind of a trend. This is a very rough sketch here, but it increases typically linearly and then starts falling down exponentially again. Okay. So, this is the intensity of a cross peak. That means, I cannot arbitrarily choose my mixing time, because mixing time has to be chosen where up to the maximum value, means I should choose either here or here or here, but not after this curve, because of T1 relaxation and other effects, that intensity now is going down. So, when intensity is going down, it will give you a misleading information. Why? Again remember, my only measurement is intensity in a nosy spectrum, and from there I have to calculate the distance by using that formula we saw in the last slide. So, if my intensity is not correct, my distance information will also not be correct. And why will the intensity be not correct? It will not be correct because as it is negative correlation, if I am increasing the mixing time beyond some duration, the intensity starts dropping. So, drop in intensity is reverse of here. So, therefore, typically we have to restrict our mixing time within this limit. And what is this limit? This is what we will see next. The limit is typically few hundreds of milliseconds. So, what happens is, suppose I have a too long a mixing time, suppose I choose very long mixing time, two things will happen. One is of course this relaxation which is going on. The second is there can be a spurious or a artifact or a wrong cross peak between two atoms which are greater than 6 Armstrongs. Remember, in nosy we should not expect cross peak between two atoms greater than this value, but I may start seeing that, and that is a phenomenon known as spin diffusion. So, let us understand spin diffusion here. So, what basically happens is, let us say I have two atoms A and there is a chain of the molecule, then there is B, then there is another chain C. So, let us say this is some hypothetical molecule, this may be between, let us say, less than 6 Armstrong, and this may be also less than 6 Armstrong. But if I use a long mixing time, what happens is this the polarization from this first gets transferred here because of the standard nosy effect. From here it gets transferred to this side here in the same during the mixing time. So, therefore, I may start seeing a cross peak between these two fellows, these two atoms, because of this intermediate B. This is similar to what we saw in Toxi, intermediate J coupling. But in NOSI, I do not expect a direct cross peak between A and C. So, if I see a cross peak between A and C in a spectrum, it will mean that A and C are less than 6 angstrom, which is wrong, because this is not, it may be more than 7 to 8 angstrom. So, you see this is called spin diffusion peak. Okay. So, this is the problem in NOSI if you use too much or too long a mixing time. So, too long a mixing time will cause a wrong cross peak between A and C, which you do not expect to see, because A to C will be long distance, but it is coming because I use such a long mixing time that the polarization jumped from here to here, then jumped from here to here. So, it looked as if it is coming from here, but that is not really the case. So, this is basically the reason why we should avoid a very long mixing time, and as written here, it is about 100 to 150 to 300 millisecond for small molecules, and we choose 60 to 100 millisecond for large proteins. For in this range if you use, then the mixing time is directly related, it comes in this side, and you can use safely the intensity as for cross peaks. So, this brings end to the 2D NOSI experiment. We will continue in the next class with the next experiment in 2 dimensional NMR, that is 2D ROSI.